So, good afternoon, everyone. My name is Aman Dhakal, and I am a graduate research assistant at West Virginia University under the Pollution Prevention Lab. And today, over the next 45 minutes, I will be talking about building energy modeling systems. This is a powerful tool used by engineers and architects to understand and improve how buildings use energy. We will explore what building energy modeling is, why it is important, the tools and techniques used, and examples of real-world applications. We will also look at the case studies showing how modeling helps achieve substantial energy savings and compliance with the standards such as LEED, ASHRAE, etc. While we won't be running any software live today, I will walk you through an example project step by step so you can visualize the process. Here is a quick roadmap of what we will cover today. We will start with an introduction of building energy modeling to why this is so important. Then we will look after some of the tools and techniques such as softwares that are commonly used in building energy modeling. After that, I will explain the different modeling approaches such as white, gray, and black box model. Then I will walk you through a software example where I will provide a detailed example of a building to share a couple of real-world case studies demonstrating measurable results. This structure will guide us logically from the fundamentals to the real-world applications. So let's get started with an introduction. To understand why do we need building energy modeling, we first need to understand what exactly is building energy. So talking about the building energy consumption, worldwide, buildings consume a huge share of the world's energy, which is about 30% of the global final energy consumption. Buildings also produce around 26% of global energy-related emissions, with 8% being direct emissions from on-site fuel and huge 18% being indirect emissions from producing electricity and heat in the heat. In the United States, the space heating alone consists of around 43% of residential energy use. These numbers makes it clear why improving energy performance is such an important part of addressing climate change and reducing operational costs. The numbers can be easily seen on the pie chart at the right side of the slide. So, building energy modeling is essentially a physics-based simulation of how a building uses energy over time. It considers the building's design, its mechanical systems like heating, ventilation and air conditioning, and lighting, the way occupants use the building, which is also known as the comfort zone of the occupants, and the impact of the weather conditions. By running hourly simulations over an entire year, these models can predict energy use, thermal comfort, and operating cost before the building is even built or before the retrofits are made. So moving to the next slide, we will discuss why the building energy modeling matters. So building energy modeling is an important aspect to boost of financial and sustainability status of any company. So if the building energy modeling is implemented well, the building energy modeling can reduce the utility bills by around 25% to 30%. Here, it is not just about saving money. It also helps ensure buildings comply with important codes and standards such as American Society of Heat and Refrigeration and Air Conditioning Engineers and IECC, which stands for International Energy Conservation Code, and also the compliance with the LEED, which stands for Leadership in Energy and Environmental Design. These savings are proven in both new construction and retrofits, making building energy modeling valuable at any stage of a building's life cycle. Now, let's talk about the usage of a building energy modeling. Building energy modeling applications leverage its ability to answer the questions that cannot be easily answered by other means. The major use cases include the following. The very first is architectural design. Some of the architects use building energy modeling to design energy efficient buildings, specifically to inform quantitative trade-offs between upfront construction cost and operational energy cost. In many cases, building energy modeling can reduce both energy cost and upfront construction cost. And second one is heating, ventilation, and air conditioning design and operation. Commercial building HVAC systems can be large and complex. Building energy modeling can help mechanical engineers design heating, ventilation, and air conditioning systems that meet building thermal loads efficiently. It also helps design and test control strategies for those HVAC systems. And the third one is building performance rating. So, building energy modeling can be used to assess the inherent performance of a building while controlling for a specific use and operation. Inherent performance rating is the basis for processes like code compliance, green certification, and financial incentives. And lastly, it is also used in building stock analysis. Building energy modeling analysis on prototype models supports the development of energy codes and standards and helps organizations like utilities and local governments plan large-scale energy efficiency programs. Now, let's talk about how energy modeling is actually done, which is the tools and techniques behind the energy modeling. We will also understand how these essential tools and techniques allow us to predict, analyze, and optimize a building's energy performance before a single brick of a building is laid. One advanced technique is called model predictive control, or MPC. It is a control strategy that predicts future loads and weather, then optimizes HVAC, lighting, storage, and DR or demand response set points over a rolling horizon to minimize the energy cost while meeting comfort constraints. This slide outlines the advanced technique of model predictive control, which moves building energy modeling from passive analysis into active, real-time optimization. Unlike traditional reactive systems that lead to high cost and discomfort, model predictive control uses a forecasting module. This module, powered by tools like Energy Plus or machine learning, which is used to predict the temperature and demand. An optimizer then calculates the most efficient control actions that maintain comfort, and this entire process repeats on a receding horizon over every 5 to 15 minutes, continuously adapting to a new data. The result is an optimized building that achieves both lower energy cost and improved occupant comfort through proactive rather than reactive management. There are several software options out there in building energy management. Energy Plus is a state-of-the-art of building energy modeling engine which is capable of modeling low energy designs and HVAC systems in addition to more conventional buildings. While OpenStudio is a software development kit that reduces the effort of Energy Plus based application development, it also includes a graphical applications that demonstrate the use of software development kit. OpenStudio has been instrumental in accelerating the adoption of Energy Plus. The third software is eQuest. which is a free building energy simulation tool which has a built-in wizard-based interface, which is designed for ease of use. This equates use WVU simulation engine. The combination of Open Studio and Energy Plus is a more modern, flexible, and detailed simulation platform where Open Studio provides the interface and Energy Plus is used to run the simulation. Now we will talk in detail about the eQuest, where eQuest is a free building energy simulation tool with a built-in wizard interface designed for ease of use. It uses the WVU simulation engine. Here's how they works. Model building is initially done in eQuest, and then we use eQuest wizard interface to define the building, such as building geometry, systems, HVAC systems, schedules, etc. Then we run the simulation. eQuest translates our inputs into a format that WVU understands. WVU performs the simulation that is built in eQuest. WVU runs the hour-by-hour calculations, example, heating, cooling loads, equipment performance, energy use, and utility cost. And finally, the results are displayed in eQuest. eQuest presents results such as charts, tables, and reports, but they all come from a DA2 calculations. We will see at the last by running a example through the eQuest where we can see some charts, tables, and reports as a result displayed. So another software is Open Studio, which is an open source energy modeling platform that simplifies Energy Plus simulations with a user-friendly interface. It supports 3D modeling via SketchUp and automation for heating, ventilation and air conditioning, lighting, and renewable energy analysis, which is an ideal for architects and engineers. It also enables efficient building performance analysis and compliance with energy standards such as ASHRAE 90.1. So lastly, the Energy Plus is the US Department of Energy's open source, which is the state-of-the-art simulation engine for modeling building physics and HVAC systems. While highly accurate, it requires a technical expertise. Open Studio simplifies this with a graphical interface allowing 3D modeling and simulation without coding. Together, they are used for everything from accreditation to LEED certification to net zero energy designs. So, not all the energy models are created equal. Basically, there are three main types, often called as white box model, gray box model, and black box model. The approach we choose depends on our goal and what are the data that is currently available. So building energy models are categorized into three distinct approaches: white box, black box, and gray box models, each serving unique purposes in energy analysis. Let's examine each model and model type to understand when and why we should select one over the others. Starting with the white box model, white box model are the most rigorous approach which uses fundamental physics laws to simulate every aspect of a building's energy performance. Tools like Energy Plus and Department of Energy 2 excel here, which offers greater accuracy by modeling heat transfer, airflow, and systems interactions in detail. However, this precision comes at a cost. These models requires extensive input data and significant computational power. They are ideal when we need high fidelity results for code compliance or cutting edge research, especially in new construction where historical data is not available. These slides introduce the white box modeling approach as a model that is based purely on the physics of the building, such as its geometry, materials, insulations, and HVAC systems, rather than on historical data. They provide high accuracy when you know the building's physical parameters and properties, but require engineering expertise and high computational power. This makes it especially useful for new construction or building owners who have detailed physical property information, as it allows for highly accurate simulations without needing past energy usage records. With adequate engineering expertise and computational resource, real estate developers can use white box models to gain valuable insights into energy performance, optimize design choices, and improve efficiency from the earliest planning stages. So, in this slide, we will talk about the simulation process in white box model. The process for a white box model is very structured. In the first principle simulation process, we solve heat mass balances for every wall, zone, HVAC coil, and control loop in the building. White box models use real physics to simulate how buildings behave rather than relying on the past data. They calculate how heat and air move through walls, rooms, and HVAC systems in detail. So to build one, we have to input climate data, building layout, and equipment specifications, which can be found from usually Building Information Modeling Files, BIM. Also, the tools like Energy Plus and Equest run these models hourly or faster, helping us to understand and test performance before the construction is begun. This slides highlights that the effectiveness of the white box modeling is a balance of its significant strength and notable demands. While it offers the highest design fidelity and it is incredibly beneficial in early design stages for creating accurate digital twins and generating comprehensive outputs for advanced strategies like model predictive control, it comes with an important considerations. Its major constraints include lengthy computational time, a heavy reliance on extensive high quality input data, and a necessity for specialized expertise to build and interpret the models correctly. Ultimately, its power is unlocked when sufficient time, accurate data, and experts' knowledge is available with us. Now, coming to this slide outlines the structured process for building a gray box model. Gray box models are hybrid which combines white box physics with black box data tuning. The goal is to develop an accurate and robust model that reflects real thermal behavior. This is achieved by physics-based templates like a 3R2C model for walls to represent thermal dynamics and setting initial bounds for parameters using engineering rules of thumb. The model is then refined through parameter identification, where advanced methods such as nonlinear regressions or genetic algorithms calibrate these parameters using real on-site data, ensuring the model balances theoretical insight with empirical accuracy. So, in simple, we start with a simplified physics model. We can think it as a simple circuit diagram for a heat flow. Then we use real measured data from the building to tune and calibrate that model. It is a step-by-step process. So basically we choose a template, we set the initial guesses, then use the algorithms to find the best parameters that make the model match reality. So in this slide, we'll talk about the gray box model again. This slide presents that the gray box model is a hybrid approach that effectively balances the strengths of the white box model and black box models. Unlike complex white box model that rely on detailed physics equations, gray box models simplify the physics for a significantly faster simulation times. By blending these easier physics-based equations with data-driven calibration, the gray box approach successfully combines computational speed with reliable accuracy, making it highly practical solution for building energy modeling where both efficiency and precision are important. For example, if there is a retrofit project with some operational data, a gray box model can quickly evaluate its heating, ventilation, and air conditioning upgrade options. Now, this slides defines the hybrid gray box modeling approach, which maintains a simplified physical structure positions itself between a detailed white box simulators and purely data-driven black box model. It is supported by tools like MATLAB, Simulink, Modelica, Python, and system identification toolboxes that uses algorithms such as genetic algorithms or particle swarm optimizations for automated calibration. Key applications include short horizon load forecasting for demand response and real-time model predictive control, where rapid in about millisecond level solutions are essential for effective operational decision making. Now we'll talk about the black box model. Talking about the black box model, it is a model that take a first data approach. It means we require the data first, where they learn patterns from the existing building performance data without relying on physics. This makes them fast to run and easy to calibrate. Though they require a substantial historical data to work effectively. Machine learning techniques like neural networks are commonly used in this model. A simple example can be a smart building might use black box models to predict next day cooling loads based on the weather forecast and occupancy patterns. Also, the black box model also have some limitations. The major limitation of black box models is their complete dependence on historical data. They cannot be created without it. So, black box model only work for buildings with existing operational data or very similar structures. Without sufficient data for calibration, black box modeling simply is not feasible. Talking about the black box model, they use machine learning to predict energy used based on inputs like weathers, schedules, and past demand, where there is no any physics involved. They are built using tools like Python, R, or MATLAB. Black box model are ideal for fast tasks like day ahead forecasting, real-time anomaly detection, or acting as a backup when physics models are too slow. So to build a black box model, we first collect high frequency building data, like every 1 to 5 minutes, for several weeks. We then pick a machine learning algorithm such as regression, neural networks, or decision trees. Then the data is split into training and testing sets, and we fine tune the model for best accuracy. As conditions change, we retrain the model regularly to keep it reliable. So, black box models are fast and great for real time tasks like control or fault detection. They require a very little upfront information and can learn complex patterns from the data. But the data they need should be highly quality. They need lots of quality of data. Missing or biased data hurts the accuracy of the model. So they are best for short-term predictions, detecting anomalies, or acting as a fast stand-in when physics models are too slow. So we learned about the three basic models. So while selecting a model, we need to be very clear. So this slide provides a clear guidance on model selection based on data availability and project goals. White box models are recommended choice when there is no any historical data, as they rely solely on physical principles and building specifications. Conversely, when the objective is to predict energy consumption using actual operational data, black box or gray box models are more suitable. These data driven or hybrid approaches are particularly valuable when detailed physical information is incomplete or unavailable, as they use statistical methods to learn patterns directly from measured performance, ensuring practicality and relevance. Now, I will move towards the use of software. Here, for this webinar, I have used eQuest as energy modeling software for building energy management. This slide introduces a practical demonstration of building energy modeling using eQuest software, which focuses on 25,000 feet square two-story office building in Charleston, West Virginia. This model simulates a typical operational setup, including a package DX and gas furnace HVAC system with occupancy limited to weekdays from 8 a.m. to 4 p.m. The purpose here is to showcase how energy modeling like eQuest can be applied to real-world scenarios, providing insights into energy use, system performance, and potential efficiency improvement for commercial buildings. This slide highlights a critical step in the energy modeling process, which is developing a three-dimensional geometry of the building. Using a software like eQuest, we create a digital representation of a physical structure, defining its shape, orientation, floor plan, and surrounding context. This geometric model forms the foundational framework upon which all subsequent energy calculations are based, including solar exposure, heat transfer, and spatial zoning, ensuring that the simulation accurately reflects the real-world building's energy behavior. Our modeling begins with geometry and zoning. Here, we have defined a rectangular footprint with perimeter core zones to capture different thermal behaviors. The perimeter zone handles external loads such as sun, wind, while the core focuses on internal gains. Notice how we have specified dimension like 15 feet perimeter depth, where perimeter depth is a horizontal distance extending into the room from the interior surface of the wall. That affects how we model heat transfer through the walls. The building envelope is the first line of defense in energy efficiency. And here we have modeled it with R19 walls, R18 roof insulation, and double pane windows. Specifications chosen to balance cost and performance for this Charleston office. These inputs directly dictate thermal loads, with the wall and roof R values resisting conductivity transfer, while the windows manage solar gain and infiltration. The table typically lists exact material layers like exterior cladding, insulation types, and vapor barriers to ensure accurate heat flow calculation. For example, a 20% improvement in envelope performance could reduce the building's HVAC energy use by 15-30%, highlighting why these details matter. Always validate input against climate specific standards like ASHRAE 90.1. For exterior doors, we have specified 4 doors, one on each side of the building, using double glazed clear tint glass in aluminum frames without thermal breaks. Each door measures 7 feet tall by 6 feet wide, which is standard for commercial office building. The glass specification of 1 by 8 inch clear glass with 1/4 inch air gap provides a balance between visibility and thermal performance. Note that the aluminum frame width of 3 inches, while common, this could create a thermal breeze that we may want to address later with the thermal breaks if energy performance need improvement. These door specifications will impact both the building's infiltration rate and thermal loads, particularly at the entryways where the foot traffic is at heaviest. For the exterior windows, we have a model 4 windows on each facade using double glazed clear glass in fixed aluminum frames without any thermal breaks. The dimension of the windows are of 5.22 feet wide by 3 feet tall, which are positioned at standard steel heights. The glass specification combines 1/4 inch clear outer plane with a 1/2 inch air gap, which is a typical commercial configuration offering good visibility while controlling solar heat gain. The window to wall ratio is 40%, where it has 50% net to ceiling that balances daylighting needs with thermal performance. Note that these aluminum frames could create thermal breezes, and we might consider thermally broken frames if energy targets require further optimizations. The uniform distribution helps maintain the consistent daylighting and thermal loads across all orientations. For activities area, we have allocated 70% of the space is at the executive offices, while the remaining 30% is divided into support spaces like corridors, conference rooms, and mechanical areas. This distribution reflects a typical professional office layout where most space is dedicated to individual workstations. The occupancy density varies significantly by area, from 2000 square feet per person in executive offices to just 50 square feet per person in conferences room during meetings. Ventilation rates are also zone specific, with higher CFM cubic feet per minute requirements in restrooms and copy rooms due to equipment and hygiene considerations. These inputs will drive both the HVAC loads and the fresh air requirements throughout the building. Also, for the interior lighting, we have implemented American Society of Heating and Refrigeration and Air Conditioning Engineers 90-point compliant standards across all spaces. Executive offices accounts for around 70% of the area at 0.8 watt per square foot, which is a conservative value reflecting modern LED efficiencies. Notice the variation in lighting power densities where public spaces like lobbies use higher 1.52 watt per square feet for aesthetic impact, while corridors are at lower 0.57 watt per square foot. The copy room has the highest LPD around 1.64 due to tax lighting needs. These values directly impact both the cooling loads and annual energy consumptions. We have also applied lighting profiles that adjust usage based on the time of a day and a season. For example, reducing lights during launch hours or weekends when occupancy is lower. For the miscellaneous load, we have modeled a fully electrified office with equipment power densities carefully calibrated to modern workplace needs. Executive office account for the majority at 0.75 watt per square foot, reflecting computers, monitors, and small appliances. The copy room shows the highest density at around say 0.7 watt per square foot due to photocopiers and printers. Note, this is concentrated in just 22% of the floor area. So, all loads are scheduled with hourly profiles that reflect typical work patterns, including after hour usage and weekend reductions. These plug loads contribute significantly to the both building's cooling requirement and annual energy consumptions, typically accounting for 25% to 30% of total electricity used in modern buildings and offices. So, for the HVAC system, we have selected a packaged single zone DX system with a gas furnace for this office building, which is a common choice for small to medium commercial spaces. The system features an 11 seasonal efficiency ratio unit and 80% efficiency for the furnace, representing baseline efficiency equipment. While this configuration meets code minimums, we will later explore how upgrading to higher efficiency options like 18 SER for heat pump could improve the performance of a building. The economizer controls the Charleston mild season by enabling free cooling whenever the outdoor temperatures drop below 65 degree Fahrenheit. That means if the outside air is cooler than 65 degree Fahrenheit and the inside need cooling, the economizer opens up the dampers to pull in that fresh cool air, which is a strategy that can reduce mechanical cooling by 15% to 20% during spring and fall. Also, the system delivers 55 degree Fahrenheit supply air for cooling and 120 degree Fahrenheit for heating, which are the standard set points that balances comfort and efficiency. Continuous fan operation from 7 am to 5 pm ensures consistent air calculations, though we could potentially save 3 to 5% in fan energy by implementing an auto shut off during unoccupied periods. So, occupied mode temperatures are cooling set point is 76 degree Fahrenheit. That means system cools when the temperature rises above this. Also, the heating set point is 70 degree Fahrenheit. That means system heats when the temperature drops below this temperature. In the unoccupied mode, the cooling set point is set to be at 82 degree Fahrenheit. That means which is less aggressive cooling than when the space is occupied. Heating set point is set at 64 degree Fahrenheit due to unoccupied mode, which is less aggressive heating when the space is unoccupied. Now, moving towards the result, this slide represents our monthly energy consumption breakdown, revealing critical patterns in both electricity and gas uses. The electric load shows a significant seasonal variation, peaking in summer for cooling from July to August, with secondary winter peaks from lighting and equipment. Notice how ventilation fans create a steady baseline load year round. Gas consumption tells a different story, which is dominated by winter space heating that demands that taper off sharply in spring. The minimum summer gas use comes from water heating only, which is a prime candidate for electrification or solar thermal integration. Now, let's analyze this detailed electricity consumption data. The table reveals several important patterns. First, the space cooling dominates summer loads, peaking at around 6700 kilowatt hour in July. Second, notice that the consistent baseload from ventilation fan around 21,050 kilowatt hour annually, and the miscellaneous equipment is around 83,250 kilowatt annually, which together accounts for around 55% of yearly energy consumption. The lighting load shows a seasonal pattern too, with higher winter usage, 4,500 kilowatt hour in January, likely due to longer operating hours. Most strikingly, space cooling alone represents 14% of annual electricity use despite only operating 6 months, while highlighting a key opportunity for energy efficiency improvements through equipment upgrades or energy efficiency measures. This table shows the monthly breakdown of a natural gas consumption for our baseline building, measured in millions of British thermal units. The majority of gas use comes from space heating, totaling up around 116 million BTUs annually, with the highest demand in the colder months, January, February, and December. The second major category is domestic hot water, which remains fairly consistent year round at 2 to 3 million BTUs per month, totaling just under 30 million BTUs annually. So other categories like heat rejections, pumps, and exterior uses are negligible in this case. Overall, the building consumes about 146 million BTUs of gas per year, which is nearly 80% of this 80% of the energy used for space heating. This seasonal pattern highlights the significant impact of winter heating loads in Charleston climate and points to opportunities for efficiency improvements in heating systems and envelope design. So, we have implemented two key energy saving strategies that demonstrate a significant potential to the Charleston building that we have taken as an example. Firstly, we reduce the lighting power density from 0.8 watt per square feet to 0.5 watt per square feet by upgrading to high efficiency LED fixtures with smart controls, which helps on reducing in both lighting energy and cooling loads. Second, we are proposing major HVAC upgrades, replacing the 11 SER DX unit with 18 SER model, which is 64% more efficient, and swapping the 80% AFU furnace to a 95% AFU condensing unit. Together, these measures target the building's largest energy consumers, lighting and space conditioning, while our earlier data showed account for nearly 60% of total energy use. Now, after implementing those efficiency measures, the seasonal energy patterns remain fairly similar, but with reduced magnitudes. Electric loads peak in summer due to cooling through, though 18 SCR equipment has flattened the curve. Gas use continues to dominate in the winter months, but the 95% AFUE furnace shows lower consumption. Now, after implementing the efficiency measures, we see dramatic improvements such as space cooling loads dropped by 52% annually from 26,820 to 12,940 kilowatt hour. Also, the lighting energy tails fell 25% from 53,740 watt to 40,000 watt from the lighting power density reduction. So we can also notice that the summer cooling peaks are now less extreme, with July consumption down from 6,700 to 3,380 kilowatt hour. The remaining loads, ventilations, and equipment now represent 61% of the total use. The overall annual gas use is around 154 million British thermal units, which is slightly higher than the baseline. While gas use increased slightly 145.8 to 153.6 million, this reflects two competing effects. The 95% furnace now meets more of the heating load efficiently, while the reduced lighting density 0.8 to 0.5 decreased some of the internal heat gains, slightly increasing the space heating requirement or demand. Now, the net result shows HVAC systems upgrade successfully shifted from electricity to gas, with total energy cost will drop, still dropping significantly due to 52% of the cooling and 25% of the lighting reductions. The upgrades delivered major electrical savings. Cooling loads dropped around 52% from 18 SCR system, and lighting fell around 25% after reducing lighting power densities. So around 6% of the gas increase reflects improved furnace performance meeting more of the heating load, compounded by reduced internal heat gains from efficient lighting. While gas use rose slightly, total energy cost decreased significantly, which showcase how strategic electrifications like future heat pumps could optimize further. Now, this is not just theoretical. Let's look at two real buildings where energy modeling was key to their success. The Copenhagen Cargo Extension showcase how building energy modeling drives sustainability in industrial projects. This warehouse in Denmark used energy modeling to become super efficient, earning the highest LEED Platinum rating. The team tested different designs and computers first to find the best insulation and air sealing options. By connecting to the city's shared heating system and carefully planning the energy use, they saved a lot of power and scored perfect marks, 18 out of 18 for the energy section. It shows even a big simple buildings like warehouse can be energy champions with smart planning. The next one is NREL Resource Center in Colorado. Their goal was incredibly ambitious. With a net zero energy building, this massive building in Colorado produced as much as energy as it uses. Here is how they did it. They used energy modeling from the very beginning to design every aspect, such as super insulation walls R40, natural ventilations, roof insulations with the help of R50, solar power, daylighting and lighting controls. NREL research support facilities showcase how even energy intensive buildings can achieve remarkable efficiency. Originally designed for net zero efficiency, the facility adapted when its data center, consuming 33% of the total electricity, threatened this goal. By implementing advanced cooling, heat recycling, and server optimization, they slashed the data center use by 84%, achieving an industrial leading of 1.2 PUE. Alongside the building's super insulated envelope and solar power, this helped maintain building 50% of the energy saving versus the cost, proving that the smart design can overcome unexpected challenges. Also obtained as a certification of LEED Platinum. So to wrap up, I want you to leave with the few key takeaways from our discussion on building energy modeling. First, the building energy modeling is a powerful physics based tool. It's not just a simple calculator, it's a sophisticated simulation tool that uses detailed data on the building's design, system, and environment to predict energy use cost and comfort on an hourly basis throughout a year. Second, we saw that there are three different modeling approaches for different needs. The white box model is ideal for new designs when you have detailed physics data but no any operational history. The gray box model offers a smart balance combining simplified physics with the real data for faster simulation, which is a perfect for control optimization. And lastly, the black box model was a powerful data driven approach for existing buildings with plenty of historical data, which is great for forecasting and anomaly detection. The key is to choose the right tool for the job based on our data and goals. Third, the software demonstration with the equation showed practical process. We walked through defining geometry, envelope loads, HVAC systems. Most importantly, we saw how building energy modeling allows us to test energy saving measures like improving lighting efficiency and upgrading HVAC equipment before any construction or investment or quantifying the potential saving and feedback. Finally, the case studies of lead, warehouse, and the NREL net zero facility prove that the real world impact. The building energy modeling is not just theoretical. It is essential for achieving high performance goals like lead certification, slashing energy use by 50% or more, and even reaching to the net zero energy. So, in conclusion, building energy modeling is a critical decision making tool. It reduces financial and environmental risks, which unlocks significant cost saving, and it is fundamental to designing, constructing, and operating the sustainable high performance buildings of the future. So these are the references I have used for the presentation. Thank you all for joining today. We'll open the floor for the questions in just a moment. But before we do, I want you to mention that if you have additional questions after today, whether about this presentation or pollution prevention in general, the best point of contact will be Dr. Ashish Nimbarte or Dr. Chris Moore from the WVU pollution prevention team. Their emails are listed here and they will be happy to help any questions or follow-up discussions. Please do not hesitate to reach out them directly.